Hello, right, I'm carrying on with the 2021 Oxford PAT. We got up to question 13. We've got a toilet roll made up of an inner cardboard tube diameter X centimetres, toilet paper wrapped around it to give an overall diameter of Y. Right, so we've got something that's looking a bit like that. That's Y, that's X. The length of the tube is Z, that's Z. Suppose the diameter of the inner tube is reduced from X centimeters to X minus 1 centimeters, but the volume of toilet paper is kept the same. What is the difference in the total volume of the roll? Right, so the total volume must be meaning including the bit in the middle, the empty bit inside the inner tube, which is maybe an interesting way to look at the volume of a toilet roll, but otherwise it doesn't mean anything. So we've got then that. So what have we done? We've started off with, so the volume of the paper is going to be pi y squared z. Oh, these are diameters though, so over 4, because it's going to be y over 2 as the radius, minus pi x squared z over 4. So that's our volume of paper that we've got, and this is staying constant. So we're going to need to get what the new y value is. They've given us the new x value being x minus 1. So that is going to be equal to pi times y primed squared, that's our new y, times z over 4, minus pi times x minus 1 squared times z over 4. So we can cancel a lot of 4s, a lot of pi's, and a lot of z's. So that's going to leave us with y squared minus x squared is equal to y prime squared minus x minus 1 squared. And what do we want to work out? We want to work out the difference in the total volume of the roll. So delta V is going to be equal to, what is that going to be? That's going to be pi y squared z over 4 minus pi y prime squared z over 4. So that, again, we can probably cancel quite a few things. Oh, well, now we can't cancel the pi's and the z's and everything, can we? But let's factorize them and we'll see. So we need to do a y squared minus y prime squared. But we can get that out of here just by rearranging. It's going to be x squared minus x minus 1 all squared. So that's pi z over 4 x squared minus x minus 1 squared. So the x squareds are going to cancel, and it's going to leave us with minus 2x plus 1 multiplied by minus 1. So that's pi z over 4. What did I say? Minus 2x becomes 2x, and plus 1 becomes minus 1. Okay, that wasn't too bad. It was quite a lot for 3 marks, but nothing out of the ordinary, really. A machine requires 10 kilowatts of electric power when operating at 100 volts. Okay, so that means we're going to have, R is going to be 1 then, it's going to have a resistance of 1 ohm just off of that, because it's V squared over R is the power, so 100 squared is 10 kilowatts. Right, if power is delivered through a cable with resistance 100 ohms, how much power is lost to the cable's resistance? Right, okay, so we're going to have, if it's so if it's delivered through this cable, we're going to have 100 ohms to 1 ohm, pretty much. That's our machine is the 1 ohm, the cable is that, so we're going to get 100 times the voltage, and then we're going to be dividing by 100 times the resistance, but the voltage is squared, so we're going to end up going up. It's going to be 10 kilowatts multiplied by 100 squared over 100, which means we're going to get 1 megawatt. That is a serious amount of power loss. But there you go. That's what we end up with. In order to reduce power loss, yeah, good idea, a transformer is used between the cable and the machine. What ratio of turns is required on the transformer in order to reduce power loss on the cable by a factor of 10 to the 4? Right, this is going to be, I always find transformers easier to think about in terms of current. I don't know why. So we've got that. So we want the power to be, we're reducing it by a factor of 4. We got 10 to the 6. So we want to get the power down to 100 watts, which is going to be I squared times R, which means, and R is 100. So we need to get 1 amp running through all of that. So if we need 1 amp, but in the machine, we need 100 amps. So we need to go from 1 amp in the cable to 100 amps in the machine, which means we're going to need a 100 to 1 turn ratio in order to step up that current in that way. Right, another fairly straightforward question. The observed brightness of a sun-like star shows periodic dips. The time period between these dips is 225 days. If the dips are interpreted as being transits of a planet in a circular orbit around the star, estimate the radius of the orbit. You may assume that the star is the same mass of the sun and that the planet's mass is much smaller than the mass of the star, as in it's not moving around. We can consider the star to be stationary at the focus, and we haven't got like some double orbit thing going on. You can take the mean radius of the Earth's orbit of the sun to be that. Right, okay, so we're going to have, let's get this in circular motion language then. So let's try and squeeze something on here. We'll have m r omega squared will be equal to gmm over r squared. That's just our F equals ma for circular motion. So we can cancel a few things. Well, we can cancel 2 things. And we can also say that omega is equal to, well, it's 2 pi f, 2 pi over t. That's our omega. So we're going to have, off of this, there's not much space on this particular one, so I'll go over here. R cubed is going to be equal to gm multiplied by t squared over 4 pi squared. So that is that. And then what are we trying to work out? We're trying to work out r, the radius r of the orbit. So, well, we can ratio these things for, because we haven't put in anything specific to an orbit here. So we can have one for Earth and one for not. So we can say r Earth cubed divided by r cubed is going to be equal to t Earth squared over t squared. So really, this is just doing Kepler's law, Kepler's third law, but I've worked it out at the beginning. So we've got this, and we want to get r cubed. So r cubed is going to be equal to t squared over te squared multiplied by re cubed. So, well, they've given us re. We know that t is 225 versus 365.25 for the Earth. So all we have to do is tap all of this in, get a number out of it. So it's quite a lot to type in though, annoyingly, which is why I'm waffling on while I'm typing it into the calculator, and it comes out 1.086, so 1.09 times 10 to the 11 meters. So that's what you'd expect, a little bit closer for a shorter orbital period. So not bad for 5 marks. A model of the transit and its effect on the star's brightness is shown in the figure below. Assuming that we observe the system in the plane of the planet's orbit, okay, draw the relative positions of the planet and the star at times TA to TD. Calculate the radio of the planet and the star. Right, so we want to draw the pictures and then work out radii. Right, okie dokie. So, and we have to draw these pictures at all 4 of these times. So, as it depends. Well, let's draw it as it is as you'd be looking at it from the Earth. I don't know whether they're wanting some kind of 3D sort of type picture, but I'm not going to bother doing that. So at TA, this is when it it first starts get a dimming coming in at this point. So when we get to TA, we're going to have the star and we're going to have the planet just touching the edge, touching one edge. And then at TB, that means we've now got into the area of full dimming. We're at the minimum point here. So that means we're going to have now got the star, that should be the same size, but we're now going to be inside. And then at TC, we've still got full dimming. So we're going to be like that. And then at TD, we're going to be back out the other side. So we look like that. So off of all of that, we should be able to work out what all of these bits and bobs are then, right? So let's write these things down so I can scroll a little bit more. So delta T1 is 23 minutes. So that's while the planet is in transit on the edge, on the limb of the star. And then delta T2, we've got 10.5 hours. Right, so I can scroll down a bit more. We got to work out, what are we working out? Oh yeah, the radii of the star and the planet. Right, so let's work out then 23 minutes is going to be 23. What was the orbit of this thing? The orbit is 225 days. So 23 minutes is going to be 225 times 24 times 60. That's going to be our denominator of an orbit. That's the fraction of the orbit that it is, which means we've got a distance. So the distance will be 2 pi r multiplied by all of that thing. So 2,3 over 225 times 24 times 60. So that's the distance that it's moved in 23 minutes. So what does that mean? We've gone through the distance is the diameter, isn't it? So we've just worked out r as well, haven't we? So, because yeah, I should put that as maybe as a capital R on all of that. So we've got, what was that? That was 1.09 times 10 to the 11. So we got 2 pi times 1.09 times 10 to the 11 times 23 divided by 225 times 24 times 60. And that is the diameter of the planet. So let's type all of this in. That's quite a lot again. So we got 2 times pi times 1.09 times 23 is equal to that, divided by 225, divided by 24, divided by 60, gives 4.86 times 10 to the 7. Now I need to halve that. So the radius of planet is going to be equal to 2.4 times 10 to the 7 meters. Right, okay, so that's, yeah, what's that? 24,000 kilometers, so about 6 times the Earth. So we can do the same thing pretty much for the radius of the star, can't we? Because we're going to be, nearly. But we have to remember, because, yeah, this 10.5 hours is going from inside edge to inside edge. So we're going to have to add on a diameter of the planet as well, aren't we? In order to make it the full diameter of the star. So if we add on a radius of the planet, we'll get the radius of the star. So yeah, we can just do exactly the same thing here. So do it again, 2 pi times 1.09 times 10 to the 11. But now we've got to multiply it by 10.5 hours. So that'd be 10.5 times 60 plus the 23. And then divide it by the 225 times 24 times 60. And then that will give us the diameter of the star. Right, I really shouldn't have hit clear on the calculator because I could have just gone back and replaced the numbers, but I didn't think of doing that. So what we got, 10.5 times 60 plus 23, stick all of that in brackets, do that, divide by 225, divide by 24, and then 60, and it's given, oh, and then I need to halve it. So that's come out as 6.9 times 10 to the 8. So radius equals 6.9 times 10 to the 8 meters. Oh, that was quite a full-on question. But yeah, not bad. There's a bit of interpretation to do there, and it would probably be quite easy to lose this 23 here and not get the full diameter of the star, but otherwise that wasn't bad. Right, so let's push on to question 16, wherever it is. I gave a lot of working out space for that. Question 16, a vehicle travels in a fixed direction at a velocity v, function of time, varies with time as follows. So we've got 3 different time domains and 3 different velocity functions. Right, a, b, c and v2 are constants. Find a, b and c such that both the velocity and acceleration are continuous at t equals t1 and t equals t2. Right, okay, let's start with velocity then. So for the first one, we'll have first boundary a, t1 squared is equal to c minus b, t1 minus t2 squared. All right, second one, we put t2 in, oh, we just get c is equal to v2. Right, so that's pretty good. Oh, so that means we're also going to get nothing for the acceleration at that boundary. So we're only going to have one acceleration boundary then. We're going to have 2a t1. This is the only one we're going to get any information out of. It's going to be minus 2b t1 minus t2. Excellent. So, all right, let's start solving these. So let's eliminate b then. So get rid of that, get rid of that. We can say that b is equal to minus a t1 over t1 minus t2. So that's good. Sub that into this equation here. Gives us a t1 squared is equal to, well, that's going to be v2 for c, minus, well, that'll become a plus, a t1 over t1 minus t2. Oh no, we've got t1 plus t minus t2 at the top is what we should have. Yes, that's right, yeah, because yeah, we've got 1 that I'm dividing by here and taking the 2 off the top. So that's good. That's going to give us a, isn't it? So we've got then off of this, let's scroll down a little bit more because I don't think we're going to need that anymore at the top. So I can then follow downwards. So we've got a t1, which is going to be multiplied by t1 minus t1 plus t2 is equal to v2. So a is equal to v2 over t1 t2. B will be equal to, oh my word, right, so that's going to be, so just putting it into this one here, so we've got a minus a there, so we're going to have a v2, the t1s are going to cancel, and at the bottom we're going to have a t2, and then if I make that t2 minus t1, it gets rid of the minus sign, and then c is equal to v2. Right, that's a bit of a fiddly mess around, but it wasn't that bad. Sketch the velocity and acceleration as a function of time. So we've got to sketch these things in these different areas. Right, so velocity is only going to be positive, so we don't have to worry about that too much. So we've got t1, t2, and then we've got the acceleration, which is just, well, that's going to be in these different areas as well, these different domains. So what did we have for, so the velocity we ended up at, what did we end up at? v2. So we got an at squared and then a minus quadratic and then a constant. So we're going to have that for the first bit, that for the second bit, and then flat. And that's going to be v2. And then for the acceleration, so what did we have? The acceleration for the last bit is just 0. For the first bit is 2at, so we've got a straight line going up here. Then we've got, that's going along 0 there. And then we've got acceleration of that is minus 2b times, all right, so it's a negative straight line. And it's continuous. Yeah, we know these things have to be continuous. So if it's a negative straight line, everything's continuous. It has to join up the ends of the other points. Otherwise, it wouldn't be a straight line that's continuous. So that's fine. Now what have we got? Find the total distance travelled. Oh, you're kidding me. Between t is 0 and t is t3. Right, total distance travelled. So we've got to work out the area under all of this. So what were our functions? We got at squared. So at squared. So this means we've got the integral of, well, a is v2 over t1 t2. That's a multiplied by t squared dt. And that goes from 0 to t1. So we've got that. And then the next one was c, which is v2, so c minus b, so v2 minus v2 over t2, t2 minus t1, multiplied by, well, that was t minus t2 squared, wasn't it? So t minus t2 all squared. Right, that's that dt, and that's going from t1 to t2. This is going to be just so tedious. And then what was the last bit? It was the, oh, we're just moving at v2 for t3 minus t2 seconds. So t3 minus t2 times v2. Good grief. So yeah, so we've got to do all of these integrals. Ugh. So that's going to be, well, at least the 0 isn't going to come into it. So we'll have v2, t1, t2. Then that'll be t1 cubed over 3. So that's our first term. The last term is fine because that isn't going to change. We've already got that sorted. It's this bit in the middle that's going to be really annoying. So, yeah. Okay, we're going to have... Oh, you're kidding me. I mean, it's just horrible. I suppose we've got the integral there of v2. So let's do it in 2 bits because that bit's on its own and then we've got all of this bit. So that's going to be v2 t2 minus t1. And then we're going to have to take off this mess of a thing. So minus, well, let's make it a plus and switch the limits around. So we'll be going t1 at the top and t2 at the bottom. Oh, when it's t2, we're going to get 0. Because when we put it into here, this bracket is going to come 0. So we just got a t1. So yeah, we just got one term. Right, okay, so that makes it easier. We're going to have a v2 over t2, t2 minus t1. We'll have to have a third of that to deal with the power being raised, and then we'll have a t1 minus t2 cubed. So it's all of that, which I think, considering how ugly it is, and how many marks are we getting for that? 4 marks. Do I want to simplify that? I don't know if there's much simplifying we can really do, is there? I mean, maybe there is. Is there anything? Well, you know what? I don't want to do any. Oh, we've got, yeah, I suppose actually we got an easy win off of the second term and the last term because the v2 t2s are cancelling. So we've got v2 t1 cubed. Oh no, the t1's gonna, yeah, we do have to cancel because that's going to cancel at the bottom. Oh, good grief. Right, okay. v2 t1 squared over 3t2. That's our first term. v2 t2s are cancelling, so we're going to have a v2 t3 minus t1. And then we're going to have, does that do anything, that one? Oh, we got T2 minus T1 will cancel if we put in a minus sign. V2 over 3T2 multiplied by T1 minus T2 squared. Okay. Well, that's just it's a bit of a lame question, really. I mean, there's no insight going into that last bit. It's just slogging through a horrible amount of calculus. Hopefully I've done that right. I mean, I could easily have made a mistake in all of that, but really I don't particularly care. Even if I've made a mistake, it's not going to be anything insightful in any of this. So if you spot anything, let me know. But, you know, it seemed as though it went okay. So let's just go with that. I'm going to leave those questions there after that one. I think I need a bit of a break and then come back in the next video.